Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will try to discuss about the introduction to quadrature phase shift keying. These are the outlines. We'll start up with the introduction where we will try to describe that how we can represent our PSK signal in terms of energy and power. Then we will describe various features of quadrature phase shift keying, what basically quadrature phase shift keying is, which will be followed by the mathematical analysis of quadrature phase shift keying. Then we will going to show the signal space diagram of QPSK signal, and finally we will going to conclude via describing the signal space diagram of 8PSK. Two major constraints in the field of communication system are, that is your transmission power and the bandwidth. So whatever communication systems we have discussed so far, we always demanded that there should be low transmission power and it should consume lower amount of bandwidth, so that with the help of lower bandwidth we should be in a state to transmit much larger amount of information. So can we achieve more data rate with the use of same amount of bandwidth, whether it is possible or not? So yes, it is possible with the use of MRE signaling schemes. So what do we actually do in our MRE signaling schemes is, instead of transmitting a single bit information, we will basically going to combine several bits in a group, and then we will going to send those groups of information. By this manner, we are in a state to transmit much larger amount of information over the same bandwidth. So till now we have discussed several binary digital modulation schemes such as ASK, PSK and FSK. We had already gone through the generation as well as the detection methods of these types of binary digital modulation schemes. So now we will going to discuss our quadrature phase shifting, but before we will going to discuss, let us quickly understand that how we will going to express our PSK signal in terms of its energy as well as power. This exercise would have been important just to understand the QPSK in much more better and efficient way. Simultaneously, it will also be helpful when we are going to refer different sort of books where the generalized expression of QPSK waveform would have been given in terms of energy and power. So if we consider phase shift keying modulation scheme, in PSK, for transmitting one bit of information, we are actually transmitting our carrier signal A cos omega ct, and for passing our information bit 0, we are actually transmitting A cos of omega ct plus pi, which is 180 out of phase with the previous carrier signal. So this is how our PSK modulated waveform can be expressed. So the mean square value of the above cosine waveform would have been given as we know that the mean square value can be evaluated with this expression, that is equal to 1 upon 2 pi, integration starts from 0 to 2 pi, a square cos square omega ct dt. So mean square value, I mean first we need to take the square of the given signal, then we have to take its mean value, or we could say that the average value. Since our cosinusoidal signal is a periodic signal with a period of 2 pi, that is why we are taking the average during that time period. So here A is the peak amplitude and P represents the power of the signal. So A is your amplitude. So this could further be rewritten as power is equal to A square upon 2 pi, integration starts from 0 to 2 pi, 1 plus cos of 2 omega ct by 2 times of dt. So we just have applied this cos 2 theta formula, which states that 1 plus cos 2 theta upon 2, that will be equal to cos square theta. So we have applied that simple formula. So now further solving, so we just have taken out this 2 outside, and what we are left with, integration starts from 0 to 2 pi 1 times of dt plus integration starts from 0 to 2 pi cos of 2 omega ct dt, which would have been solved as, for this 1 times of dt we will be having 2 pi minus 0, that will be equal to a square upon 2 times of 2 pi into 2 pi. Since integration between 0 to 2 pi cos of 2 omega ct dt will be equal to 0, so the complete outcome of this whole expression turns out to be p is equal to a square upon 2 times of 2 pi into 2 pi minus 0, which is your upper limit minus lower limit.
So what we are left with is P is equal to A square upon 2. So just because power is equal to energy per unit time, we can also write this as P is equal to E upon T. So that expression would have been written as A square is equal to 2 times of P. It means A is equal to under root of 2 times of P. So in terms of energy, it would have also been written as A square is equal to 2E times of T. Here E is representing the signal energy and T is representing the signal duration. So A would have been also been equivalent to A is equal to under root of 2E by T. So hence we can represent the PSK wave like St is equal to under root of 2p times of cos of omega ct. So in place of A we have written this under root of 2p for bit 1, and for bit 0 in place of A we have again written this under root of 2p. So that turns out to be minus times of under root 2p cos of omega ct. It means for transmitting 1 bit we are sending under root of 2p cos of omega ct signal, and for transmitting 0 bit of information we are passing minus root 2p cos of omega ct. So which is 180 degree out of phase with the previous carrier signal. So since there exists a phase difference of 180 degree between two symbols, that is why we are calling them as a phase shift keying. So in terms of energy, it could further would have been rewritten as St is equal to under root of 2e by t cos of omega ct. So we have put this under root of 2e upon t instead of a from this particular expression. So for passing 1 bit of information, we are actually transmitting the signal under root of 2e by t cos of omega ct in the similar manner, and for transmitting 0 bit of information we are actually passing a minus times of under root of 2e by t cos of omega ct. So all these things are same. So this exercise is quite relevant just because when you will going to follow different sort of textbooks, then the generalized expression of QPSK in some books it would have been written as in terms of energy, and in some books it would have been written as in terms of power. So I hope now you will be in a state to understand it properly how that generalized expression is written. So quadrature phase shift keying. So what is quadrature phase shift keying? So quadrature phase shift keying is a form of phase shift keying in which two bits are modulated at once, selecting one of the four possible carrier phase shifts, that is 45 degree, 135 degree, 225 degree or 315 degrees. So quadrature phase shift keying is a special type of your phase shift keying in which instead of transmitting one bit of information as we do in our PSK waveform, we are actually grouping the two number of bits together, and then we are selecting one of the four possible carrier phase shifts to pass that group of information. So it is again a bandwidth conserving scheme, which is the example of your quadrature carrier multiplexing scheme. So if you just recall that in our quadrature carrier multiplexing, we are also doing the same thing. We are actually passing two different types of message signals over the carrier signals which are 90-degree phase apart. So that was your analog modulation scheme. Your quadrature carrier multiplexing is your analog modulation schemes, but your QPSK or quadrature phase shifting is your digital modulation scheme. In quadrature carrier multiplexing, you are transmitting two different message signals, that is your M1 and M2, whereas in your quadrature phase shifting, you are transmitting the digital symbols. So that is why we are calling it your quadrature phase shifting as a digital modulation scheme. So QPSK allows to signal to carry the twice as much information as ordinary PSK using the same bandwidth. So since instead of transmitting only a single bit, we are simultaneously transmitting a group of two bits. So that is why it is having the twice data carrying capacity in comparison to your PSK signal. In QPSK, we are grouping two successive bits, and then the combination of these two bits forms four distinct symbols, such as with the combination of two bits we can form four distinct symbols such as 00, 01, 10 and 11. So that is why we are saying that it is forming four distinct symbols whose values are represented as 00, 01, 10 and 11. That means we are combining these two bits as one symbol, these two bits as second symbol, these two bits as a third symbol, and these two bits as a fourth symbol. So instead of transmitting our information likewise 0 and 1, we are transmitting our information in terms of these symbols only. So the generalized expression of this QPSK signal can be given as the QPSK signal Sn of t will be equal to under root of 2 ps cos of 2 pi fct plus phi of t. So we had already seen that this under root of 2 ps terms basically signifying your amplitude term, and this basically representing our QPSK signal. So here cos of 2 pi fct plus phi of t, where phi of t is representing the phase angle. So the phase angle phi of t can be given as 2n minus 1 times of pi by 4, where n can take these values 1, 2, 3 and 4 only. So here in this particular expression, our ps is representing the symbol power and this phi of t is representing the phase angle, which is given as 2n minus 1 times of pi by 4. So the generalized expression for QPSK signal can also be given as Sn is equal to under root of 2 es by ts times of cos of 2 pi fct plus pi t. Now you might be able to understand that why we have performed that exercise, so that we could understand it quite properly. So amplitude in terms of energy can be given as under root of 2 es upon ts. So where es is the symbol energy and ts signifying the symbol duration. Obviously we are talking about the energy and duration of those group bits. So phi of t will be equal to 2n minus 1 times of pi by 4. So for different values of n, we will be having different phase angle. So n could take the value of 1, 2, 3 or 4. When we're going to put n is equal to 2, then we're going to get the phase angle value that will be 3 by 4. And for n is equal to 3, we will be having 5 pi by 4. And for n is equal to 4, we will be having the phase angle value of 7 pi by 4. So from trigonometry, we know that formula cos of a plus b turns out to be cos a cos b minus sin a sin b. So cos of a plus b can be expanded with this particular form. So what we are trying to do is we will try to expand this particular equation cos of 2 pi fct plus phi of t in terms of this expression. So from that thing we can expand that signal, that will be equal to under root of 2 es upon ts times of cos of 2 pi fct cos of phi t minus sin of 2 pi fct sin of phi t, where this phi of t is actually representing the phase angle, which could take any values as we discussed in our previous slides, that is your pi by 4, 3 pi by 4, 5 pi by 4 or 7 pi by 4. So from this expression we can observe the following things. First of all, this QPSK signal can be composed of two orthonormal basis functions such as phi1t and phi2t as cos of 2 pi fct and sin of 2 pi fct, since the angle between this cos of 2 pi fct and sin of 2 pi fct is 90°. That is why we are calling them as a orthonormal basis function, or in simpler terms we could say that we can express our QPSK signal with the help of two orthonormal basis functions. So what is so peculiar or specific about our orthonormal basis functions is, first of all, they will be having unit energy, and second most important point about our orthonormal basis functions is they possess 90-degree phase shift to each other. This could be quite visible with this expression, that the angle difference between cos of 2 pi fct and sin of 2 pi fct is pi by 2. So since there is a pi by 2 phase shift, that is why we are calling them as a orthogonal functions. So these two orthonormal functions phi1t and phi2t can be expressed as phi1t is equal to under root of 2 over ts cos of 2 pi fct, t lies between 0 to ts, and phi2t can be expressed as under root of 2 over ts sin of 2 pi fct. And these two orthonormal basis functions are 90-degree phase apart, that is sin t and cosine t, there exists a 90-degree phase shift. As I had also discussed about the specific property of orthonormal basis functions is it is having unit energy. So the amplitude of under root of 2 over ts actually making their energy unity. So you can simply evaluate the energy in the duration of ts of this particular signal, you will get the result as unity. So this is a small mathematical exercise. You can perform it at your own. So there are 4 message points and associated signal vectors which are defined by. So what are those 4 message bit points? That is, we had already mentioned 00, 01, 10 and 11. So these are your 4 message points and associated signal vectors which could have been defined as Sn is equal to under root of Es cos of 2n minus 1 times of pi by 4 and minus of Es sine of 2n minus 1 pi by 4. So if you closely observe the previous expression, it is having the same thing. So what we actually did here is we have separated our orthonormal signals, and whatever we are left with, we have written in here. So this is actually expressing our bit value, that is 1 or 0, and in combination of ones and zeros we are calling them as a symbol. So for different values of n, we will be having different phase angles. As we discussed in our previous slide, for the value of n is equal to 1, we will be having the phase angle as pi by 4, and for n is equal to 2, we will be having the phase angle as 3 pi by 4, and for n is equal to 3, we will be having the phase angle of 5 pi by 4, and for n is equal to 4, we will be having the phase angle of 7 pi by 4. Here Es representing the symbol's energy. So Gram-Schmidt orthonormalization procedure states that any vector in the signal space can be represented as the linear combination of basic functions. So if you have gone through this Gram-Schmidt orthogonalization procedures, you have already studied that. In that case, it is quite easier to understand. But in such case, if you haven't studied about Gram-Schmidt orthogonalization procedure, in simpler word, we can also say that we are trying to represent our composite QPSK signal in terms of linear combination of two basis functions, that is your phi1t and phi2t, which are orthogonal to each other. So in general, this is what I'm trying to tell you. So now the nth QPSK signal based on the message points SN1 or SN2 defines in the tables. So this particular table is actually being defining the different coordinates of our message points in terms of various phase angles in radians. So before discussing whatever has been given in this particular table, I just want you to just focus on this particular expression where Sn is equal to under root of Es cos of 2n minus 1 pi by 4, and the second bit of the symbol is being written as minus under root of Es sine of 2n minus 1 pi by 4. So this was the generalized expression. For different values of n, we will be having different values of bits. So for n is equal to 1, what phase angle do we going to have is, now putting this n is equal to 1, we'll be having 2 minus 1, that will be equal to pi by 4. So for n is equal to 1, we will be having the phase angle of pi by 4. So when we're going to put this phase angle pi by 4 in the generalized expression, the first symbol's bit 1's energy or amplitude can be written as under root of Es by 2 as this, and first symbol's second bit can be represented as minus times of under root of Es upon 2. So here this Sn1 and Sn2 are basically representing the actual bits in the symbol. So what signifies this? N is actually representing the symbol. So here we have taken n is equal to 1. So in the first symbol, the first bit's energy can be written as under root of Es upon 2, and the first symbol's second bit can be represented as minus under root of Es upon 2. In the similar manner, when n is equal to 2, the phase angle turns out to be 3 pi by 4, and when we're going to put this value of phase in this particular expression, what we are left with, S of 2 of 1, that will be equal to under root of Es cos of 3 pi by 4, that will be equal to minus times of Es upon root 2. So this minus sign basically signifying that we are actually transmitting zero value of information, and this plus under root of Es upon 2 is representing that we are transmitting our 1 bit. So in the similar manner, for n is equal to 3, we will be having minus under root of Es by 2 and under root of Es upon 2, and for n is equal to 4 we have under root of es by 2 and under root of es by 2. So these are basically the coordinate points of our message signal. This is basically representing the combination of the two bits as a symbol as given by this particular expression. Sn of t will be equal to Sn1 times of phi1t plus Sn2 types of phi2t, where phi1t and phi2t are nothing but these are your orthonormal basis functions, and Sn1 and Sn2 these are nothing but they are signifying the nth symbols bit 1 and nth symbols bit. As we already discussed in our last slide, that what we are actually trying to do is with the help of orthonormal basis functions we are trying to pass our information bit as Sn1 and second bit as a Sn2, and the combination of both this Sn1 and Sn2 which will be forming a group of bit to which we are also calling them as a symbol. So with the help of these two orthonormal basis functions we are trying to pass that symbol. So this particular figure is showing the constellation diagram of QPSK. So constellation diagram is nothing but it is the two-dimensional vector space representation of signaling units. So here we will be having two orthonormal basis functions phi1t and phi2t, and these particular points, these particular purple points are actually showing the several message. So since we had already mentioned that there are four possible combinations via combining two bits simultaneously, that is your 00, 01, 10 or 1. So the distance between this origin to that particular point is actually signifying its amplitude level, and this is actually showing the angle. So on this complete circle we will be having the same strength or amplitude value that is equal to its radii, and here its amplitude will be equal to under root of es by 2. So there are basically four possibilities, that is your 1 1, and this is your third message point, that is your 01, this is equivalent to 00, and this is equivalent to 1. So here the angle between any two consecutive message point is pi by 2. It means the angle separation between this message point to this message point is pi by 2. Then again this message point to this message point, this is again your pi by 2, and so on. So each and every consecutive message points, the phase separation between them is pi by 2. That is why we are also calling them as a quadrature phase shift keying, since the difference between any two consecutive message points is pi by 2. So this is how the constellation diagram of QPSK looks like. We'll be having four message points, that is your MP1, MP2 and MP3 and MP4, where each message point consists of two bits whose magnitude will be equal to under root of ES. So the higher order PSK would also be possible. The constellation usually deals with the binary data, which means that the number of symbols is usually a power of 2 to allow the integer number of bits per symbol. So this is quite obvious since we are talking about digital communication systems and it is made up of only these two combinations, that is either 0 or 1. So we can have number of symbols that are power of 2, that is 2 to the power 2 to the power 3 to the power 4, which will be analogous to having 4, 8 or 16 different number of symbols. So any number of phases may be used to construct the PSK constellations, as we discussed that either it could be 4, 8, 16 or 32, but the important point is it should be the multiple of 2 to the power of n. So if we use more number of phases than 8, then the error rate becomes too high. Although high number of phases would also be impossible, and generally in our 4G systems we are using 64 PSK modulation. So there are better though more complex modulation schemes are also available, such as our quadrature amplitude modulation, which we will going to discuss in our upcoming lectures. So this particular figure is showing the constellation diagram of 8 PSK. So where we have divided our complete phase angle of 360 degree into 8 equal parts, and here the angle between two consecutive message points is 2 pi by 8, that will be equal to pi by 4, that is 45 degrees. So this is how the constellation diagram of 8PSK looks like. So in our next lecture, we will try to discuss how do we going to generate QPSK signal. Hopefully you will get the insight about the QPSK signal, how its constellation diagram looks like. These are the references. Thank you very much for your patient hearing.